When the discriminant of the characteristic equation is positive, then the value of lambda will be straightforward. And I think you have known that when the discriminant is positive, we will obtain two real values for the lambda, or for the root of the equation. And from there, we can obtain two different solutions for the differential equation. So it is quite clear in this case. However, when the discriminant of the characteristic equation is 0 or negative, then things might look a bit more complicated. Let's start by talking the case when the discriminant is negative. And from the lesson that we've got in high school, when the discriminant is negative, then the root of the equation will be complex numbers. And we can check this by looking into this example. Yeah. Okay, so this is the equations, a differential equation actually, and this is also second order linear differential equation. And yeah, by assuming that the solution will have an exponential form, something like this, and then substituting this into the original equation, we will obtain the characteristic equation. Then we want to check the value of the discriminant here, which is the 1 square here, 1 square minus 4 times 1 here and times 1 here. So the value of the discriminant is 1 minus 4 equals minus 3, and this is negative. So the two value of the lambda will be here minus 1 plus square root of the discriminant divided by 2, and also the value of the second lambda, this is also minus 1. Now this is minus. Okay, and as you can see here, lambda 1 and lambda 2 are complex. So we can also, then we will obtain the solution for the for the equation here. Then the solution will be an exponent of a complex number. So let me erase this first. Yeah, and then I will write the the solution of the equation. So this is the exponent of, let me simplify the value as well here. Okay, so I use I here to replace the minus 1, and the second solution will be exponent of is minus. Okay, so it is actually alright to write the solution like this using a complex number, but if we are asked to write the solution in a more simplified form, then we can apply some formula that have been described in the book. This is the formula related to complex number. This is called the Euler identity, this one here, or Euler formula. And if you search in YouTube, then you will find that this Euler identity has been considered as one of the most weird formula in mathematics. So this formula can be obtained from from the Taylor expansion. From the it is actually described in this article from the Taylor expansion of the exponential function, and in the end we will obtain this Euler identity. Yeah. Okay. So we can also employ this Euler identity to rewrite our solution for the differential equations here. Okay, so because we have I here, so I can write this to okay. So we can use Euler formula to replace this this term in here. Okay, so this is the the other form of the first equation for the first solution, and for the second solution I also have I can also rewrite things similarly here. Yeah. Okay, so this is the the second form of the the the, the, the second solution that has been rewritten using the Euler formula. Okay, so yeah, you can also notice that we've got cos minus, but you know that cos minus just equals to cos cos the positive. So I can actually remove the minus sign here, and also from the sign here we also have minus, so we can actually just take out the minus from within the sign, so this become positive, but then here the symbol here will become minus. Yeah, so this is the new form of the two solutions of the differential equations.